Hi, welcome to part 2 of the video series Deriving Euler's Number. Today we're going to talk about 3 topics that are going to be helpful with the actual derivation of E or Euler's number. The first topic is what are functions, the basics of functions. The second is inverse functions. And the third is the fundamental theorem of calculus. I had talked about the fundamental theorem of calculus very briefly in my previous video. Today, I'm going to talk about it in a more detailed manner. So let's start off. Let's start off with our first topic, which is functions. Now, to start with this topic, I'm first going to start by talking about the lifetime of a tree. So if you see, a tree starts off as a seed, and then as you keep watering it and it gets sunlight, it grows into a sapling. As its age increases, so does its height. It goes from a seed to a sapling to a plant and eventually to a full-grown tree. So you could say that the height of the tree is dependent on age, right? Now let's think of age as something called a variable. Now, what is a variable? A variable is something that varies, as the name suggests. But to understand it better, let's say this, that age is a word that represents a number which can keep changing. So today, if the plant is 5 days old, age could be equal to 5. Tomorrow, if the plant is 6 days old, age could be equal to 6. So this representation of a number and that keeps changing, whose value keeps changing, is a variable, right? So you could say that the age of the tree as well as the height of the tree are both variables because they both these words represent values that can keep changing. And we said that the height is dependent on age. So in mathematical terms, we could say that the height is a function of the age of the tree. So height is equal to, let's represent this function or this dependency as f. F is a conventionally used letter. You could use G, you could use H, you could use anything. But we are going to say f of a. Let a be the variable that represents age. So let a be, I'm just taking single letters because that's more conventionally used, but it's your choice. So we could say that f of a represents the height of the tree, saying that this height, which we're representing with the function f, is dependent on this variable called age, which we're representing with a. And let's just say the height is equal to 2 times a. It's not true. That's not true with respect to the earth, but this is just an assumed equation that we're creating. So this means that the height of the tree is 2 times the age of the tree. Therefore, let's say a is equal to 5 days, for example. Then we could find out the height of the tree by looking at f of 5, which is equal to 10. And we could say that it's 10 centimeters, for example. 10 centimeters is the height of the plant. This is a function, something that shows the dependency of a certain variable on other variables. Now let's have a look at more regular examples. Let's have a look at speed. So we know that speed is equal to distance by time. So let's represent speed as a function called s. And s is dependent on both distance and time. Let distance be represented by d and time be represented as t. So you can see over here, s is dependent on two variables. Therefore, we put a comma in between within the parentheses. could say that S of d comma t is equal to d divided by t. Now, based on the values that we substitute for or we assign to d and t, we get the value of this function or the value of speed. Another example could be the price of a house. Price of a house. You could say that the price of a house is dependent on the number of rooms that the house has, the floor the house is on, and the square foot area of the house. So that we could say P, let's call that function P of number of rooms, let's represent it with R, square foot area by SQ, and floor with F. And this could be equal to some equation involving these three variables. Yeah? Okay. So now let's move on to inverse functions. This is a very interesting topic and very important for the derivation. And we'll get to know why very soon. Okay. So what are inverse functions? To understand that, I'm going to write down a couple of functions for you. Let's say f of x is equal to x plus 5. And another function g of x is equal to x minus 5. Now, the reason why I've used the same variable is that it's allowed. Because the variable's value keeps changing, it's completely fine to use the same variable or represent a variable with the same letter in both these functions. It's just that the two function names f and g cannot be the same because f and g are different in its character. So it's doing something very different to this variable x. It's like you could say that the width of a tree is also dependent on the age of the tree, but very differently. Okay. Okay. So now, let's say that x is equal to 3. Okay. And let's pass this value to f. So f of 3 is equal to 3 plus 5. We're just substituting x with 3, which is equal to 8. Now let's pass 8 through g of x. So g of 8 is equal to 8 minus 5, which is equal to 3. So if you notice over here, we started off with 3. We passed it through f. We then passed the result to g, and we got back 3. So we could say that f and g are inverse functions because what one does, the other undoes. So to represent it even better mathematically, you could say, so we first used f of x. So f of x, and we're passing f of x into g as the variable. And this gives us back x. Okay. Now, why did we talk about inverse functions and how is it going to be important with our derivation? There is a beautiful example of inverse functions, which are exponentials and logarithms. So let's understand that better. Let's say now f of x is equal to, let's take the base 5, so 5 raised to x. And g of x is equal to log of x with the base 5. So over here, let's first say x is equal to 2. Let's pass 2 to f. So we get f of 2, which is equal to 5 square, which is equal to 25. Now we pass 25 to g. So g of 25 is equal to log of 525. And here we ask the question, how many times should 5 be multiplied to itself to get 25? 2. So you see, we started off with 2 and we came right back to 2. So whatever f did to 2, whatever result it gave us, g undid that result and gave us back the original value 2. Okay. Now let us move on to the fundamental theorem of calculus. And in front you can see a couple of diagrams. We're going to first discuss these diagrams, and with the help of these examples we're going to understand this theorem. Okay, so let's have a look at it. Let me change the color of my pen first. Okay. So here in front of you, you have two cases. Case 1 is of this student who is very disciplined in nature. He lives 900 meters away from his school, and whenever he walks to school, he walks in a very regimented way. So it's exactly 30 meters that he walks every single minute. Now, if he walks 30 meters every single minute, what does that mean? It takes him 30 times, 900 by 30 minutes to reach there. 900 by 30 meters per minute to reach there, which tells us that it takes him a total of 30 minutes to reach his school, right? Now, if you notice, if he walks 30 meters in the first minute, 30 meters again in the second minute, it also tells us one more thing. It's telling us that there is a relation between the distance covered by the student and the time taken. So in the first minute, he covers 30 meters. In the second minute, or after 2 minutes, he completes 60 meters, right? And so on. So we could say that the distance covered by the student is a function of the time taken. It's a function of t, which we're going to represent time with t, and is equal to 30 times t. Is that right? Yeah? Okay. Now let's go to case 2. Now the student in case 2 is after my own heart. He doesn't really want to go to school. So what he does is he also is 900 meters away from school, but he lingers around first. In the first minute, he only walks 1 meter. In the second minute, he walks 3 meters. In the third minute, just 5 meters. So you see, slowly the distance he's covering with each minute is increasing. And eventually he runs to school because he realizes he's really late. Now let's analyze this. We see that in the first 1 minute, he walks 1 meter. In the first 2 minutes, he walks 4 meters. And in the first 3 minutes, he walks 1 plus 3 plus 5, which is 9 meters. So now do you see a sort of relation between the distance and the time taken? Any guesses? Exactly. So the distance here is again a function of time and is equal to the square of the number of minutes taken. So therefore you could also say that it takes him 30 minutes to reach school, which is 900 meters away, because 30 square is equal to 900. Now do you notice something? Both these students have taken 30 minutes to reach school, right? But are their methods of going to school the same? So just by knowing that they spent 30 minutes to travel 900 meters or had an average speed of 900 divided by 30, which is equal to 30 meters per minute. Does it make, can you say that these two are exactly the same because they both have an average speed of 30 meters per minute. Doesn't make sense, because if you even look at the graph, let me just show you a graph showing their movement. You can see that one is a straight line because it shows how consistent student 1 has been. Once again, let me just highlight it. So this is case 1. You can see how slowly and constantly the distance is increasing with time. So time is the x-axis, distance covered is the y-axis. And with each minute, 30 meters more is covered. But look at case 2, look at student 2 over here. You can see that the distance covered keeps increasing exponentially as the time increases. So they have different graphs. They have different ways of going to school. But just their average speed, checking just the average speed over 30 minutes does not really give us this information. So let's decrease the interval a little bit. Let's talk about 15-minute intervals. Okay, one second. So you could say that student 1 between 0 to 15 minutes walks 30 times 15, which is 450 meters. And similarly, between the 15th and 30th minute, he walks 450 meters again. Now let's have a look at student number 2. Between the 0th and 15th minute, he walks 15 square, which is 225 minutes. Now between the 15th and 30th minute, let's think of how you could calculate something like this. We'll take a longer route, which will eventually help you with the approach used in the later parts of this topic. Okay, so when 30 minutes have passed, he walks 30 square meters. And when 15 minutes have already passed, he walks 15 square meters. So we need to remove the distance walked after 15 minutes from the distance walked in 30 minutes total. And this is equal to 900 minus 225, which is equal to 675. So this time you see, you have a better description that in the first 15 minutes, student 1 has an average speed of again, so 450 divided by 15, which is equal to 30 meters per minute. And it's the same even for the next 15 minutes. So in both the intervals, student 1 has walked 30 meters per minute. But have a look at case 2. Case 2 gives us a better understanding. You can see that in the first interval, student 2 has walked a smaller distance, and in the second interval, he has walked a much larger distance. So decreasing the interval has given us a little more information, but not the complete information. We still don't know the exact way that these two students are walking to school. So let's decrease the intervals now. Let's decrease the intervals further. Let me just remove this so that you can see it clearly. Okay. So do you see this? Intervals of 10 minutes. This time, in 0 to 10 minutes, you can see that the average speed of student 1 is always 30 meters per minute. But then look at student 2. Let's look at student 2. That's the interesting case over here. That helps us understand if this interval is going to help us understand more about how student 2 is walking. So have a look at this here. Once again, sorry. The color is not red. Okay, so have a look at it here. Now you see in the first 10 minutes, the average is 10 meters per minute. Next 10 minutes, it's 30 meters per minute. And the last 10 minutes, it's 50 meters per minute. So much more information on the way the second student has walked. So we see that decreasing the interval time but increasing the number of intervals helps us understand the graph better. So let's decrease it further. This time, if you see, we've decreased it to 5-minute intervals. And you'll notice that student 2, the average speed, is slowly indicating exactly the way he did walk to school. So in the first 5 minutes, it's 5 meters per second. Next 5 minutes, it's 15, and then 25, then 35. So you can see the slow increase in the speed. Okay. Now that we've decreased the interval even to 5 minutes, just think if we decrease the interval to just a minute. It would make so much more sense. That's what we had initially started off with. But even 1 minute is a long period of time. How did those students walk within that 1 minute? How did they step around? Did they take circles? How do we understand that? Maybe if we decrease the time interval to a millisecond, it would give us so much more information. And that is what leads us to the fundamental theorem of calculus. Let's look at student 2's graph. This is student 2's graph in front of you. And let's take a time t1. So t1 is a time stamp. This means at t1, the student has walked t1 squared meters, right? And let's assume another time stamp t2. And at t2, he has walked t2 squared meters. Now, the relation between t1 and t2 is this, that t2 is just a very small amount away from t1. So we have really decreased the time interval to maybe a millisecond or a nanosecond. So you could say that t2 is equal to t1 plus a very small number which we'll represent by h. And we could say that h tends to 0 or its limit tends to 0. This means that h is a number that's so close to 0. So you can see that t2 and t1 are hence very close to each other. We could also say that the interval is equal to h. So t2 minus t1 is equal to h, which is again close to 0. This means that t1 and t2 can be represented using just t1. Let me show it to you over here. Let's see. So you could say that t2 squared, you can come over here, can be represented as t1 plus h the whole squared. Now, this means that the distance covered between t1 and t2 would be the total distance covered at t2, subtracting the total distance covered at t1. Exactly what we did in our 15-minute intervals. We're doing the same thing over here. Now, to understand the average speed, we need to divide the distance covered in the interval t1, t2 divided by the time taken in t1, t2, which we saw was h. Therefore, the average speed or distance covered is t1 plus h the whole squared minus t1 squared and the whole thing divided by h. So you could also represent it as f of t1 plus h minus f of t1, right, divided by h, wherein the limit of h is 0. And if you see, this is basically the fundamental theorem of calculus. Let me take you to the formula here, written properly, and that is dy by dx. So y here is just equal to distance, which is also equal to f of t. And we say that the momentary change in y or in the distance or f of t, when we look at to very close values of t is the derivative of that function. Yeah? And this is where we conclude with the fundamental theorem of calculus. In our next video, we're going to find the derivatives using this theorem. We're going to find the derivatives of exponentials and logarithms. Okay, then that's it for today. Thank you, and I hope you have a great day ahead. Bye bye.